Okay, let's begin. So what I was telling you about last time was about orthogonal matrices. So we're going to spend most of today talking a little bit more about them because there are many things that you can say about them. Again, I'm calling them. I will call these matrices U just because they're also called unitary matrices if you allow for complex numbers. But so it is a square matrix. So here I have a matrix of size n by n, and so that makes us a square. What makes this orthogonal or unitary is that if you take you can take any two vectors of size n, compute their dot product, and the number that you get, right? Remember the dot product is a number. The number that you get is the same number that you would get if you multiply a vector by the matrix U and then compute the dot product. So that means that the dot product remains the same before or after like you do the multiplication by the matrix U. Okay, so that is a definition. That's actually like the definition even if you allow complex numbers. It's just that when you allow complex numbers, what changes is like the definition for the dot product. You have to fix it a little bit so that it's still kind of useful. But I mean, that's something that we're not going to get into. But so there's like a modified version of the dot product when there are complex numbers involved. And in that case, the matrix is called unitary instead of orthogonal. But it is like kind of the two notions agree if you're just looking at things with real numbers, which is what we're doing in this course. Okay. This in practice is not that useful to check because it's a condition that you wouldn't have to check for any vectors of Rn, right? So what you do in practice, like we worked that a little bit like last time, is that this is the same as checking, okay, or determining if U is orthogonal, is the same as checking that if you do U transpose times U, you get the identity matrix of size n. So that's an easy condition because that's just like a matrix multiplication. So for us, like being orthogonal means that when you do U transpose times U, that is the identity. That's the best way to check that a matrix is orthogonal. Is that okay? Any questions about this? In particular, I think we mentioned this briefly. There is already a matrix in general that has a property that if you multiply by the given matrix, you get the identity, right? Like that's a defining property of the inverse. So what this is saying in particular is that an orthogonal matrix is invertible and its inverse is just a transpose. Okay, so let me give you some consequences of this formula. So some properties of orthogonal matrices. So the first one, which is useful, is that U is invertible. and U inverse equals U transpose. Okay, so for orthogonal matrices, finding the inverse is very easy. You just transpose it, and that's the answer. Another property, which is pretty straightforward, we can discuss it, is that the determinant of U has to be plus or minus one. So that's also nice to have. I'll just write the statements and give you like a mini proof. Like the proofs are quick, so I'll just write the statements first. Uh, and the other one is the proof. I can do it. I mean, okay, yeah. Let me write this. If D is a vector, D is any vector, then the length of the vector UV is the length of the vector V. You'll see, I mean, it may be clear or not at the moment that this happens, but that means that when you multiply a vector by the matrix U, the length of that vector does not change. Okay, so one way to say this is that U preserves length. And the last one is that the fourth property that I want to mention is that if lambda is an eigenvalue of U, then lambda is plus or minus one. If U has real eigenvalues, oh, then lambda equals plus or minus one. Okay. So these are the four key properties of orthogonal matrices. Let's see why they are true. So the first one I kind of already mentioned it. It just follows from this property, right? Because that's precisely what it means to be like the inverse, right? Like the inverse is a matrix with that property. So that one hopefully is kind of clear. For the second one, I mean, it's not too bad. Again, you start from the key equation, which is U transpose U equals the identity. So you can take determinant of both sides, right? This is a product of determinants, right? If you remember the properties of determinant. And remember, determinant of U transpose is the same as determinant of U, right? Like the transpose does not change the determinant value. So that gives you determinant of U squared equals 1. And so that means that the determinant of U has to be plus or minus 1. That making sense? For a second. So that's second property. How about property 3? Is there well, let me, yeah, that's okay, for property 3, we need to remember like the formula for the length of a vector in terms of the dot product. So is there like anyone who remembers how can you find the length of a vector in terms of the dot product operation? Well, let's, before giving you the formula, let's try to think about it for the case of 3 entries. So this is the length of this vector, right? In terms of dot product, how could you write that? Yeah.
Oh, you thought it with itself.
Right, it's just v dot v, right? Is that making sense? So the length of a vector is the square root of the dot product of that vector with itself. Is that okay? So the length of any vector, in this case now I'm talking about the vector u v, matrix u times v, is a dot product of the vector with itself. And just to work again, this formula that this also important formula that I gave you last time. Remember that in a dot product, you are allowed to move the matrix around, but so what could you do here? If like I wanted to play a little bit with that dot product, how can I move the matrices?
One of the properties of an orthogonal matrix is that it preserves the dot product.
Well, you could just use that right away. Yes, I'm kind of re-deriving that property. What you're going to say, or I thought you raised your hand.
Okay. You can move the other side.
Yeah, it's going to be the same with what you're saying. Like, so you could just jump right ahead and say that the definition of orthogonal matrices allows you to remove these U's. But I just wanted to refer to this one because it's still on the board. So if you remember, like one of the key properties of the dot product is that you can move the one matrix to the other factor as long as you put like a transpose. Okay. And then you transpose U because the matrix is orthogonal, is the identity. In fact, this is kind of how I'm going backwards because this is kind of last time how we found this formula. So, but it's kind of like good to see it again. So this is the identity. So this gives you identity times v dot v, but the identity matrix does nothing, so you have v dot v, and so that's the length of. Okay, so an orthogonal matrix will not change the length of the vector when you do the matrix multiplication. Is that making sense? So far, so good. Yes, up to this point. Okay, and then the last property says that if the matrix happens to have a real eigenvalue, then that eigenvalue, by real eigenvalue just means that it's not complex, in the sense like there's no square roots of -1 in the eigenvalue. Again, for those who guys have seen complex numbers, so it just means like it's a number. The eigenvalue is like a number on the number line, like on the x-axis, for example. So if lambda is an eigenvalue of u, then uv equals lambda v, right? Where v here is like an eigenvector of u, right? That's like the key definition of eigenvalues, eigenvectors, where v is an eigenvector. Okay. So far so good. And the cool thing about this operation of taking the length of a vector is like it does behave kind of like an absolute value. That's why the same notation is used. Sometimes it's used with two vertical lines, but it's essentially the same, kind of the same philosophy. So you can kind of take lengths on both sides of this equation, or take absolute values if you, or magnitudes if you prefer to think about it that way. So if this is like an equality between vectors, that means that the vectors, if these two vectors are the same, their lengths should be the same, which makes sense, right? But what can I say about the left-hand side? What should that equal to? Yes, this is just the length of V, right? That's precisely what we did in property 3. So this gives you the length of V, right? So this is property 3. And this is like a number, a real constant, real number. So if you look at the formula for the length of a vector, remember you're just squaring each entry and taking the square root. So you can factorize the number out of the square root. When you take it out of a square root, it comes as absolute value. So really, this is only the absolute value of lambda times the length of v. Okay, that making sense? But since the eigenvectors are non-zero, this is a non-zero number, so you can cancel it on both sides. So you get that 1 equals the absolute value of lambda. So that means that lambda had to be plus or minus 1. Is that okay? Is that making sense? Any questions about this? Okay. So now that we have a couple properties, let's try to think a little bit more about these matrices. So to understand them better, it's useful to look at small cases. So let's try to understand all the orthogonal matrices of size 2 by 2. Okay. So let's so U is going to be a 2 by 2 matrix. There's going to be a 2x2 matrix which is orthogonal. Okay, and on top of that, just to this is actually kind of the most of the two matrices, like any orthogonal matrix has determinant plus or minus one, right? In fact, the ones that have determinant one are very important. So let's just focus on those that have determinant one. You'll see something cool happens in that case. I mean, the determinant only has two possibilities, so it's kind of we're in a sense looking at half of the case of all those matrices. So I don't know if you remember, there was a formula for the inverse of a 2x2 matrix that we did in class a long time ago. Let me just give you the formula. So a long time ago, we saw that the inverse of a 2x2 matrix had like this particular form, right? Since I'm taking the determinant to be one, it kind of, I mean, this determinant has to be plus or minus one, but I'm assuming that the determinant happens to be one so that I can ignore this first factor. So since determinant of u equals one, this simplifies to this. Okay. So far, like the only property of being orthogonal that I have used is that I can replace this denominator that appears here with one. Nothing else has been used at the moment. So I have only used property 2 here. Is that okay? But these 4 properties, right? There's also another one that's kind of useful if you want to keep simplifying, say more information about that. So which of these 4 should I also use here to say a little bit else, something else about the matrix? I already used 2, so we can, yeah, we could use 1 because this should also agree with U transpose, right? So what is U transpose in general? In general, this is A, B, C, D, right? So by property 1, these two matrices should be the same, which is not obvious, right? Why they should be the same. So by 1, determinant of U transpose is U inverse, and so that tells you that A, B, C, D is D minus C minus B A, right? So if you compare the entries among the matrices, right? And so if you look at the first and fourth entries, right, they tell you the same information. The first and fourth entries just tell you that A equals D, right? That makes sense? And the second and third, right? The second and third, they give you that B equals negative C, right? Is that okay, everyone, so far? That making sense up to this point? So U, which in general would just be A, B, C, D, right? Because it's a 2x2 matrix. Now we can replace A with D, right? If you want. B with negative C, And I'm not going to, I mean, I cannot do anything else. I'll let D be itself and D will be itself, right? So it from having like four arbitrary entries, right? Where like they were like four numbers. In fact, so far now it has been reduced to being completely specified by two numbers. Is that making sense? Which is good progress, right? It kind of constrains what like the orthogonal matrix has to look like, but there's something else that you can say. Well, the determinant of U from this formula is D squared plus C squared, right? But that should be equal to 1 because we're under the assumption that the determinant of this matrix is 1, right? So which two numbers have which two expressions have the property that when you end up together, their squares together, you get 1? There's an identity, famous identity. There's something squared plus something squared equals 1. Right, cosine squared plus sine squared equals 1. So let's just call t cosine of theta for some angle, right? And t sine of theta. And that tells us something cool, which means that this matrix was cosine of theta minus sine of theta, cosine of theta, right? But hopefully you recognize this matrix. This is our first matrix that appear in the course, our good old rotation matrix. So every 2x2 orthogonal matrix is nothing but a rotation. Okay, so let's put that as a theorem. Every 2x2, every 2x2 orthogonal matrix U corresponds to some rotation matrix. Okay. Is that making sense? So that's kind of cool because that does tell you all the possibilities about that kind of clears out the air. Like if you wanted to know what are all the possible 2x2 orthogonal matrix with determinant 1, they're really not they're essentially the same as all the possible rotation matrices you could come up with. Is that okay? Is that making sense? So far, so good. Okay, let's move to something that's even more cool, which is the 3x3 case. Euler's theorem. Okay, so here this is also cool. So imagine that you take an object like an iPad, something that's rigid, right? So in these mechanics courses, like you will talk about rigid bodies. A rigid body is one that doesn't that kind of preserves a distance between its parts. So like when you like are working with a rigid body, like over time, it's not that it won't shrink or expand or anything like that. So like, with an iPad, if it's rigid, like, any 2 points on the iPad remain at the same distance, even as you translate it or things like that. This book is not rigid, right? Because, depending on how you move it, like maybe these two things will get closer, right? So like the distances are not preserved. But rigid bodies are kind of very useful. And there's a theorem by Euler that says if you have a rigid body and you move it in some way, right? But you move it in such a way that at least one point remains fixed, right? So you're not allowed to translate it, because if I translate it, I moved every single point. So you have to do something that preserves an operation where the point, at least one of the points on that tablet, remains in the same spot in space. So what Euler's theorem says is that any such motion is a rotation about a certain axis. Okay. And that's very cool. And that gets translated into the following statement that says that so let me explain how this is going to be connected to what I just said. So what in terms of linear algebra, what Euler proved was that here's what Euler proved. Any 3 by 3 orthogonal matrix with determinant 1 um, has an eigenvalue equal to 1. And okay, I'll give you the proof because it's very elegant, very cool. And then after I give you the proof, I'll explain why this is related to the rotation stuff. Maybe obvious or not, some of you, but it is not too bad to see you know, uh, once we talk a little bit more about what it means to have an eigenvalue equal to 1. Okay, so who remembers how do you check what did you have to do to find eigenvalues of a matrix? What the equation that you had to solve? Right, so in this case, it would be our matrix is not being called A, it's called U, right? So it's determinant of U minus lambda I equals 0, right? That's what in general you have to solve for to find the eigenvalues. But now I want lambda to be equal to 1, right? If I want lambda equals 1 an eigenvalue, so for lambda equals 1, right? Like what we need to see, right? We need to show that determinant of U minus I equals 0. Is that making sense? So if we prove that the determinant of U minus I equals 0, that is telling you the lambda equals 1 is an eigenvalue. That making sense so far so good? And now the thing is, like, I don't know anything about the entries of the matrix, right? So it's kind of different from the other examples we have done so far, where I give you like a concrete matrix and you set up this equation and set it equal to 0, right? So we have to argue why this determinant should be 0. So it has to be something kind of clever because we don't know anything about the entries of the matrix. You could try to do something like kind of similar to the 2 by 2 case, but it's a little bit more messy because the inverse of a 3 by 3 matrix is a lot more complicated. I mean, you won't find something too illuminating if you try to do the same. So, but you can do this trick. Okay, the determinant of this, remember the determinant of a matrix is the same as the transpose, right? So this is the same as determinant of U minus I transpose. Is that okay? I have done nothing, right? I just transpose every matrix and this is okay because that's one of the properties of the determinant. It doesn't change if you transpose like everything, right? But what is the transpose of a difference of matrix? That's just U transpose minus I transpose, right? Is that making sense? What is let's see. Let me see how I want to say it. I'll say it this way. Okay. Right, like the identity is its own transpose, right? Yeah, this will work. But what was the definition of orthogonal matrix? Or what was the condition for orthogonal matrix? That U transpose U equals I, right? So let me just replace that in here in terms of where I is. Is that okay? Now what do you want? What should you do? What can you do? Yeah.
Common factor.
Right. There's a U transpose I can factorize, right? This proves our huh. Is that okay? So, and a product of matrices, the determinant of a product is a product of the determinants, right? So this determinant of U transpose times the determinant of I minus U, right? Does that make sense? What is the determinant of U transpose? The transpose has the same determinant of as U, so this is determinant of U, right? Times determinant of this, but let me factorize a -1. Right, so this is fine. I mean, this, like if you factorize a -1, this is okay because it gives you negative U, you have there, and negative with negative becomes plus. So this is the same. But what is determinant of U? Determinant of U is 1 by assumption. And midterm 2 question, how do you pull out a constant out of the determinant?
-1 to the third counter.
Right, -1 to the third because this is a 3 by 3 matrix. Huh. So this gives you minus the determinant of U minus I. So what have you found? That the determinant of U minus I equals minus the determinant of U minus I. When is a number equal to minus itself? When that number is zero, right? That's the only number. When is a equals negative a? When a equals zero, right? Because you can say that then to the determinant of u minus I equals zero. So the determinant of u minus I equals zero. That makes sense. Any questions up to this? And so, this is so, that means that there's like in value one, right? So let's relate this to this rotation stuff. So what does it mean to, there's an eigenvalue one? It means that u times v equals lambda v, but now lambda is one, right? Because that's the eigenvalue, so it equals one times v, so that's uv equals v. Okay. So you can, if you want, or so we call this eigenvalue. So here v is the eigenvector, right? To this eigenvalue. So we call this eigenvector omega. So that means that u omega is omega. Okay. But what does that mean? That means that this is a vector that remains the same before or after you do the multiplication by u. So when you have a vector in space, this is the same before omega is the same as u omega. Okay, but if you have a vector, you can look at all the vectors that are perpendicular to this one, that forms a plane. So this is a plane made, this is actually what is called like a normal vector for those who have taken multivariable calculus. Plane of vector perpendicular to omega. And the thing is like the matrix U, right? Remember the matrix U preserves dot products. So since a vector that's perpendicular, so if you have a vector on this plane that's perpendicular, that means that they're perpendicular. So that means that their dot product is zero, right? Because that's what it means to be perpendicular. But U preserves this equation. So that means that U times U, it times U omega should also be zero. But U omega is omega. So that means that U dot omega equals zero. So that means that U that's like terrible labeling. This continues to be a vector perpendicular to omega. is still on that same plane. So essentially what like I'm trying to say that the effect of multiplying a vector by u, essentially what it does is just change where the vectors on the plane are, so you can identify with that with the rotation. So because the length hasn't changed, so it is kind of like a 2x2 rotation, like the plane is two-dimensional. So it's kind of like essentially the same as the result that we were talking about before, that any 2x2 orthogonal matrix is a rotation is more or less the same because the plane is two-dimensional. So when you look at what the matrix U is doing on these vectors, like they're just rotating it. So you can identify, I mean, it's kind of like what one of the things Euler did. If you want, like you I can identify this vector with the axis of rotation, and the magnitude of the vector, you can set it up equal to the angle of rotation. So that's why you can also think of rotations as vectors. And this is also related to like angular momentum and other things like that you see in physics. But it is like a very cute thing to. So any 3x3 rotation, right, any 3x3 orthogonal matrix is really like a rotation about some axis. And that axis, like again, its magnitude is kind of giving, you can choose it so that its magnitude gives you the angle of rotation. So that's like a useful way to parameterize, to specify rotations in space in terms of an axis and an axis. So this is like a rotation. So you rotate the vectors on the space. Any questions about this? In fact, let's see if I can show you this. I mean, there's like a cool result, which is very fun, but I won't like always find the temptation to mention it because it would take me too much time to explain. But actually, you can write this U as an exponential matrix, and then the thing that goes into the exponential is kind of like the angular momentum of the system. That's very cool. But like if you went back to kind of like this rigid body stuff, but yeah, this is kind of too much, I think, for today. I mean, like I still have to tell you other things, but there's like a very cool formula that writes like an orthogonal matrix as an exponential of a matrix, which I really like. Right, and then those of you who, let's see. Yeah, then you can go to Wikipedia, or if you want to learn more about it, or I can find like a useful Google YouTube video. I may have some. I will mention it. I will like ask you to watch it. But then you can say, well, like to specify this vector, you could specify it by saying the angles that this vector makes with each of the axes. So if you think about it in that way, you start talking about what's called like Euler angles. Which is like a way to specify rotations in space, which is very useful. This is also used in aerodynamics and other things. Yeah, so you can go down the rabbit hole if you want to understand a little bit of how to specify rotation in space. Also, like there's an airplane or something like that here. And then there's something fun that happens as well, which is called the Kimball log. Which again, I think there might be some cute video on YouTube that I'll try to see if I can show it to you. But I mean, yeah, we need to reread about it to remember what the explanation is like. But it has to do with this thing about the rotations, but of how you specify rotations. But it's also useful. I mean, this is used on airplanes and other things. So yeah, so this is actually related to many things. So Yeah, if I find a good video, I'll make you watch about it if you want to learn about this. Takes just, I mean, so you have seen like. But you have seen that, we have seen now that, in the 2 by 2 case, a 2 by 2 orthogonal matrix with determinant one is a rotation. In the 3 by 3 case, an orthogonal matrix with determinant one is like a rotation because for L there's angle theorem. And so it kind of makes sense to call any n by n orthogonal matrix with determinant one a rotation. Okay, so you kind of like imagine, well, like something similar has to happen in higher dimensions. So I kind of think makes sense to think about this like as this matrix is as a generalization of what it means to rotate something in space. Okay, so just to give you a definition. So here's the definition. An n by n orthogonal, an n by n matrix is called a rotation matrix. Matrix. Let's call this matrix is R for rotation. If it is orthogonal, R is orthogonal. So that means that R transpose R equals identity. And the second condition is that the determinant of R equals 1. So like a rotation matrix is just any orthogonal matrix whose determinant equals 1. That makes sense. So it kind of makes, I mean, because of these two examples, it's like these two analyses that we did, it does make sense to like to single them out of I mean, if you want to know like what happens if the determinant is 1, is that the -1 is that there's some reflection involved. So there's kind of like a mirror, it's kind of like more or less like a rotation, but you also are reflecting or looking at the mirror image with respect to some plane. So the orthogonal matrices with determinant -1 are not that different from these ones, but it's not just like a rotation. So there's there is some sort of reflection happening. With like the reflection is what changes the determinant to -1 because it kind of changes like a left hand into a right hand. So that changes like the orientation of space. Or those, if that makes sense. Okay, so maybe today. So a very useful result is that, which is, I mean, may not be clear, it definitely shouldn't be clear in the definition. But a very useful result is that the product of two rotation matrices is a rotation matrix. Okay. So this is an important theorem. If R1 and R2 are two rotation matrices, then then R equals R2, R1 is a rotation matrix. So what that means, for example, in the 3x3 case, okay, let me give you a second to copy this. So in the 2x2 case, it's hopefully kind of obvious because a rotation matrix was just kind of by an angle, right? Like, so imagine like you rotate by alpha, then you rotate by beta, rotating alpha and then beta should be just like rotating alpha plus beta, right? So rotations, in fact, in 2x2 case, they even like the angles of rotation add. But you should think that this is kind of like non-intuitive, non-obvious in 3 dimensions. Because what this is saying is like, if you take an axis of rotation and you do whatever rotation you want about that axis, and then you rotate that system about a different axis by a different angle, that's the same as having done like a single rotation about a third axis, right? That's actually one of the things that Euler proved, among other things. So what this is saying is like rotating about one axis and then a second axis is the same as a single rotation about a third axis. And then like a cool thing is like, how do you find this third axis in terms of the given 2 axes? That's why you need to have like useful formulas to specify a rotation in space. And that's where like these Euler angles kick in, because you have to understand a little bit better how to actually describe rotations concretely. But you should really think it's not obvious. But like the proof is so easy from the linear algebra point of view, because what do we have to check? We just have to check that the determinant equals 1, right? And that R transpose R equals the identity. So let's start with the easiest one, right? What is the determinant of R? Is the determinant of R1, R2 times R1. But this determinant is multiplied, right? So it's just the determinant of R2 times the determinant of R1. This is 1 times 1, right? Because each one has determinant 1 being a rotation matrix. And that's just 1. Okay? Is that making sense? So it wasn't too bad. And then so that's the second condition that you have to check, but it's kind of easier because it's just like properties of determinant. And then the other condition that you have to check is your orthogonality condition. That if you do R transpose R, you get the identity, but what is R transpose R? Well, R transpose is R2, R1 transpose, right? And R is R2, R1. Right, but what is the transpose of a product? Is the product of the transpose reverse. So this is R1 transpose, R2 transpose, R2, R1. So far, so good. And now what can you say? There's an obvious simplification, hopefully, that happens now. Is there anything we can simplify using the fact that R1 and R2 are rotation matrices?
R2 transpose times R2 is just identity.
Right, this is the one in the middle one is just identity because this is a rotation matrix. So you get R1 transpose R1, and that's also again identity because it's a rotation matrix. So you just get identity. Okay. Is that making sense? Okay, so yeah, this is kind of what I wanted to say about orthogonal matrices. Practice like they're very interesting. They will be used like I think next time I want to start from scratch with the next topic next time because it's kind of starting it right now it wouldn't make a lot of sense because it's one of the biggest theorems of linear algebra. So that's called the spectral theorem. That's the one we were going to talk about next time. That says that if you have a matrix which is symmetric, then it can always be diagonalized. That's very, very important, but the diagonalization is even better than how I'm just saying it. Because the diagonalization can be done using an orthogonal matrix. So we have to talk about that. And then I'll tell you about right. I'll tell you we have time of how that's related to certain things like spectroscopy, like how do we identify chemical elements using eigenvalues of matrices. That's kind of how like quantum mechanics started when Heisenberg realized that you could if you have an atomic, if you have an element like hydrogen, they will emit light at certain frequencies, only at certain discrete frequencies. And what Heisenberg realized is that you could associate a matrix to understand that process, and the eigenvalues of that matrix kind of gives you the wavelengths of the light that you can measure. So this is how he really discovered the matrix multiplication laws and a bunch of cool things. So I'll see if yeah, that's a cool topic, and it's gives you a different perspective of how this all works. So yeah, but next time I'll tell you what the spectral theorem says, and then after that, maybe we'll do one or two more topics and finish the semester. I mean, like the rest, if we have more, definitely we'll have like classes for review. But like if we do spectral theorem and orthogonal subspaces, so like two more topics, that's kind of like I feel like what the course should contain. So I'll give you probably like a study guide for the final very soon, probably early next week. Yeah.
Do we have an official date for the final?
Oh yeah. It's which group are you? Oh, you're like group 9. I think it's on the 9th in your case. Did you check one of the announcements on linear algebra? Didn't I send on Canvas? I think I sent one Canvas announcement saying what the date for the final is, and it should be on this classroom, like just like the regular meter. So yeah, that should be fine. And as I said, for the final, you will be able to bring the formula spreadsheet. So I'll give you more details about that. But yeah, I'll probably start working on the study guide sometime next week, because now I just wanted to wait to have like a better idea of what to include or not include. But yeah, we do have a date already. So yeah, I'll see you on Monday then. And we'll talk about the spectral theorem that day.